Okay, so here's some introduction to the simple pendulum.
Good morning, everyone. Welcome to our lab sessions, our virtual lab sessions for our Physics 2 module. So obviously our labs are going to be slightly different this year. So we'll try our best to ensure that you get a good learning experience out of the labs this year as best we can anyway. So the lab we're going to start off with this year is the simple pendulum. So we've spoken a bit about periodic motion and simple harmonic motion and the movements of pendulums in the theory class. So let's just think about those two terms before we start. So we're saying the simple pendulum will move about its rest position, exhibiting periodic motion. So what is periodic motion? Let's think back to our definition for periodic motion. Excuse me. So periodic motion, as we know, is a repetitive cycle of motion which repeats itself over and over again in a given period of time. So we have a cycle of motion which repeats itself over and over again in a given period of time. So what is simple harmonic motion? So simple harmonic motion is simply a type of periodic motion. In other words, it's a repetitive cycle of motion which repeats itself in a given period of time. But in this case, it has a restorative force, a force which would return it or restore it to its rest position. So that's the definition for simple harmonic motion. Periodic motion where a restorative force acts, and that force always acts in a direction which would pull the body back to its rest position. Now today what we're going to do is we're going to examine simple harmonic motion for a simple pendulum. And we're going to use the simple pendulum as a means of determining the acceleration due to gravity. So let's look for a moment at the simple pendulum to see what we had said about that. Okay, so we had looked at this diagram of our simple pendulum in our notes. So what we have is our simple pendulum, which is a thin thread or string, in this case a spherical bobbin or bob or weight at the end of the thread, and that's allowed to move backwards and forwards in a repetitive cycle of motion, just as we would expect for a grandfather clock or something like that. So what we have here is the rest position. So if the pendulum was allowed to come to rest, it would end up in this position. So the pendulum would stop in this position, known as the rest position, or the equilibrium position, and I'm calling that position B. This position here, position A, which I'm saying is the point of maximum positive displacement. So I'm saying this direction is positive displacement. So it's maximum positive displacement from the rest position. I have this sign positive for displacement. Why do I have a positive sign? I have a positive sign because I know that displacement is a vector quantity and therefore has a magnitude as well as a direction. And I'm calling that point A, and of this point C here with point of maximum negative displacement. And again, I'm saying that it's negative displacement, it's in the opposite direction to positive. And I'm giving it a negative sign to show its direction. It doesn't matter which one we call positive and negative as long as we have two different signs. And I'm calling that point C. So if I look at one complete cycle, one complete vibration for my pendulum here, I'm going from position A. So if I pull my pendulum out, I'm going from position A down through position B, out to position C, back down through position B, and out to position A. So I have a cycle. And what I'm going to want to do today is I'm going to want to measure the time frame for that cycle or that vibration. Okay, so I've got I'm moving from position A to position B to position C, down through position B and back to A. So one complete cycle or one complete vibration, and the time taken for one complete cycle or one complete vibration is the periodic time. And that's what I'm going to want to measure today, the periodic time for this motion. Now I would also notice that, or if I thought about my pendulum there, I thought about the force acting on the pendulum. When the pendulum's to the left-hand side of position B, then the force acting on the pendulum will be in the direction of the red pen there. It'll always be pointing towards B, whereas if I have a negative displacement on the right-hand side of the line B, the force acting on the pendulum will always be in that direction. So in other words, the force always acts in a direction to pull the pendulum back to the rest position. Now, if I was to consider, and we did look at the displacement of the pendulum with time, so if I was to release the pendulum or think of it at position B, 0 displacement. If it was to move out to position A, point of maximum positive displacement, back down to position B, 0 displacement, out to position C, point of maximum negative displacement, back down to B. So I'm beginning to see a wave form if I look at displacement versus time. And we said that this distance here, the distance from the rest position to the point of maximum displacement, was the amplitude of that wave. So we have rest position point B, maximum positive displacement point A, maximum negative displacement point C. Now, so if I was to consider this, if I was to consider the pendulum again here, so if I was to consider point A, what have I got? I've got maximum positive displacement. What else have I got? I've got maximum restorative force. So the restorative force will increase as I move away from the rest position. So maximum restorative force. What else do I have out here? I have 0 velocity, so the velocity will be 0. As I move in, as the pendulum moves in, I'm seeing the restorative force will decrease and decrease and decrease and decrease until I get to here where the restorative force will be 0. I can see the velocity will increase as I move down. So at this point here, I will have maximum velocity. I will have minimum displacement, and I will have I will have maximum velocity, minimum displacement, and minimum restorative force. And as I move out, restorative force increases, velocity slows. I get to this point here where I have 0 velocity, I have maximum restorative force, and I have maximum displacement from the rest position. So that's our pendulum, and that's what we're going to study. We're looking at a cycle, and we're looking to determine the time for one complete cycle. Okay, so the next thing I want to examine now is this formula. So we're saying the periodic time for one vibration of a simple pendulum can be shown by this formula. Tau, the periodic time, is equal to 2 pi square root of L over G, where L is the length of the pendulum. So what we're going to do today is we're going to vary this length. We're going to vary this length, and we're going to use this equation to work out G for the simple pendulum at different lengths. So the first thing we have to do is we have to examine this formula, and we have to change this formula, we have to rearrange this formula in order to get G. So I've mentioned the changing the subject of the formula before, so if we're in any concern or any doubt about changing the subject of the formula, then we should go back and revise and study that. I'm just going to demonstrate it here. Okay, so I've done that transformation of the formula. So we've got our equation tau is equal to 2 pi multiplied by L over G. So the first thing we want to do is we want to get rid of this square root sign. So how do we get rid of the square root sign? We square everything. So we square everything, so we have tau squared, we have 2 squared is 4, pi squared is pi squared, and the square root of L over G squared is just L over G. So the first thing we do, get rid of the square root sign, square everything. Now I'm looking at this G, I want to get this G up to the top line. How do I do that? I multiply both sides of the equations, both sides of the equal sign by G. So I've got tau squared G multiplied by 4 pi squared L. And now when I look at this, what I want to do is I want to isolate g, so I'm going to divide both sides of the equation by tau squared, so I'll end up with g is equal to 4 pi squared over tau squared. And I can now use this formula. This is the formula that I'm going to use to calculate g today. So I'm going to use this formula to calculate g today. So let's just go through that again. So what we've done here, as we've squared both sides, with 2 tau squared, 2 squared, pi squared, and square root of L over G squared. So we'll square that to get tau squared, 2 squared, 4, pi squared, square root of L over G squared, L over G. Now I want to multiply both sides by G. So I'll multiply that side of the equation by G and this side of the equation by G. So I'll see the G's will cancel on the right hand side. So I'm left with tau squared G is equal to 4 pi squared over L. Now I want to divide both sides by tau squared. So I see the tau squared will cancel on this side. So I'm left with G is equal to 4 pi squared 4 pi squared L over tau squared. So we must we'll remember that conversion, we'll remember that formula because we're going to use that formula to work out G later on at various heights. Okay, so let's go back now and consider our method. So what we want to do now is we want to set up the pendulum as shown. So we want to measure the string at length 20 centimeters to the middle of the metal ball, to the center of gravity in effect of the metal ball. And we want to use our stop clock then to determine 50 vibrations or swings. So why are we going to determine 50 vibrations or swings? We're going to determine 50 vibrations because if we get 50 vibrations and divide by 50, then we'll have the time for one vibration. But by taking 50 vibrations, any errors that we make will be minimized. If we just try to time one vibration, the chances are we would have quite a bit of error. So we're going to adjust the string to 20 centimeters. We're going to use the stop clock to determine the time for 50 vibrations. And then we're going to repeat this experiment at 40, 60, and 80 centimeters. And we're going to fill in this table. So we're going to do it at 20, 40, 60, and obviously we would have 80 and 100 centimeters. We're going to convert that length to meters. How do we do that? We multiply by 10 to the minus 2, or we divide by 100. And then we're going to do the experiment twice at each length. So we're going to get T1 and T2. We're going to get the time for 50 vibrations, and then we're going to repeat that for 20 centimeters, and we're going to get this average. Why are we doing that? Again, we're doing that to minimize the error. How do we get the average? We add the two of these together. So we add the two of these together to get the average. So once we have that average, we've got average time for 50 vibrations. How do we get the time for one vibration? Tau. So we take our average time, we divide by 50. And just in the formula I worked out there now, I needed tau squared, so I'm just doing by tau squared there. And then I'm using the formula that we got there now to get G. Okay, so that's our basic method. Let's just look at the equipment that we would be using. Okay, so here is our simple pendulum. So we can see it is a fairly simple piece of equipment. We can see our spherical bobbin or ball here at the end. We can see our thin string, and we're supported by a retort stand. So what we'll be measuring is we'll be measuring this distance here from here down to the middle of the ball, and then we'll be swinging the ball backwards and forwards and working out the time for 50 vibrations. So we can see there we have a couple of screws there which we can use to adjust the height, and I'll just show you a picture of Paul adjusting the height. Okay, so we've got a little screwdriver so we can unscrew or loosen that, and then we can pull that string backwards and forwards. We can put our meter rule down there, which we use. We put a meter rule down here, and we adjust that height backwards and forwards to get our appropriate length. Now I just want to show you the pendulum at different positions. So we've got our pendulum here, we've got the pendulum at rest position, so it is zero displacement. This is the rest position or the equilibrium position, zero displacement. If I look now, if I move the pendulum out, we've now got the pendulum at maximum positive displacement. So maximum positive displacement, and if we let that go, it will move backwards and forwards, and we will have one cycle. So maximum positive displacement, rest position, maximum negative displacement, rest position, maximum positive displacement, or one cycle or one vibration. And there we have the pendulum at maximum negative displacement. Okay, so that's our introduction. So our